Okay, next we have Apurba Biswas from IMSC. He's going to be talking about anomalous relaxation in non-equilibrium systems.
I'll be discussing about an anomalous relaxation phenomenon that occurs in non-equilibrium systems. So I hope these two pictures will give a rough outline of my talk. What this picture shows is these two trajectories which are named A and B, and these two start from two different points, and they are approaching some common reference point which I have not shown here. So the y-axis measures the distance uh, of these 2 points as they approach the final reference point. Now the question that we would be interested in is the following. We'd like to ask if the trajectory that started from an initially further distance can overtake the another trajectory B, and we'd like to ask this type of questions in the relaxation dynamics of this kind of system. So this is a single Brownian particle which is diffusing in a potential landscape. So the questions like why this kind of relaxation is anomalous and why we are calling it as a non-equilibrium system would be clear in this talk. So this work has been done with R. Rajesh and Annapal at IMSC. Let's first consider the general scenario of relaxation that comes to our mind. So we'll consider two equal volumes of water, say, which are initially heated to two different temperatures, say 50 degree and 30 degree. Now both are cooled to a same temperature Tf, which is at 0 degree, say. Now if the process is quasi-static, I mean that if it occurs very slowly, then this kind of relaxation is very well described by the Newton's cooling law. So if delta T is the difference of the temperature of the system with respect to its surrounding, then it says that the time evolution of the temperature difference is directly proportional to the temperature difference of the system with respect to its surrounding. Now in that case, if we compute the equilibration time that the system take to relax from this temperature to the final temperature, we will find that the equilibration time increases logarithmically with the initial temperature difference of the system. So in this case, we will find that the colder system, which is initially at 30 degree, will eventually cool faster compared to the system which was initially at a higher temperature. But then there is an anomalous behavior to this kind of dynamics that was first shown systematically by Pemba. So this is a simple experiment. So he considers equal volumes of water which are initially heated at different temperatures, and then he puts them to the freezer and he measures the freezing time that all the samples take. What he found is the following result. So in this curve, the x-axis is the initial temperature of the different samples that he had prepared, and the y-axis are the freezing time that the different samples take to relax to the different samples take to freeze. What he found is a slightly anomalous behavior. So if you can see in this region, if you increase the initial temperature of the samples, you will find that they take less time to freeze. So after that, many experiments had been done, and they have found this kind of phenomena, and but they have reported different results for the occurrence of this kind of phenomena in water. So few of them are the following. So like the presence of supercooling or the presence of impurities and so on. But then in the case of supercooling, what happens is that a liquid might go below its freezing point without even undergoing the freezing. It might be still in the liquid state. So in that case, if we measure the freezing time, that will eventually give us a large time. Similarly, in the case of impurities, it might happen that it can increase or decrease the freezing time. So due to the presence of these factors, we might get an ambiguous result for the occurrence of the Pemba effect in water. And all these reasons that I told are only specific to water. So leaving behind all these ambiguities that are the reasons for its occurrence in water, we will ask a more general question in simple setups. So consider two identical copies of a system, which can be any system of your interest, say a magnetic system or a system of molecular gases undergoing relaxation, and you prepare the systems to two different initial states. So like for the case of magnetic system, you apply different magnetic field to the two systems so that they would attain different magnetization initially. And then there is a final state F here where both the systems would like to relax. So how will you attain that? So for the case of spin system, you will apply same magnetic field to both the systems so that they attain a common magnetization state. Now note that the initial state A is initially at a larger distance compared to B from the final equilibrium state. And what we would like to ask is whether the system A, which is initially at a larger distance from the final equilibrium state, can actually relax faster. Now in this kind of dynamics, when we tune the external parameters so that both the systems reach the final state, that we do it instantaneously. So this process is called quenching. When we apply that, the system is driven out of equilibrium. So this kind of phenomena has to be studied in the non-equilibrium framework rather than the quasi-static description that I had shown earlier. Now in order to study this kind of dynamics, what are the requirements for that? So as the system relaxes from one initial state to the final state, we would like to track the evolution of the system in terms of a distance function, which is a distance of the system from its final equilibrium state. And then if there is an existence of such anomalous relaxation, it would definitely show a crossing of the trajectories of the two systems as they relax towards the common equilibrium state as shown in this figure. So system A and B starts from two different points. The y-axis is the distance, initial distance from the final equilibrium, and as you can see the A is relaxing faster than B. This is just a schematic diagram. And there are certain properties that the distance function with which we are measuring the relaxation of the system, so it should satisfy certain properties. Since we are studying relaxation, so the relaxation process cannot push the system away from equilibrium. So the distance function that you define has to be monotonically non-increasing function of time. And moreover, the distance function should also mimic the initial condition that the system was initially prepared at. For example, if a system if there are two systems, one at a hot temperature and another at a cold temperature, then the distance function at time t equal to 0 for the hot system should be higher than that of the cold system. Otherwise, it can give us false realization of the Pemba effect. So, with this framework, we would like to understand this anomaly in simple setup of a single particle system, which doesn't have all the ambiguities that I had discussed for the case of water. So this system consists of a single Brownian particle. These are micron sized particles which is put in water. So this will experience the fluctuations due to the kicks from the water molecules, and the water is initially at a temperature TH. So this water acts as a thermal reservoir or a heat bath. And in addition, the particle experiences an external force due to this potential, and this kind of potential in experiments is achieved using the optical tweezers. So due to the confinement of this external potential, the particle is confined between these two positions, x min and x max. Although the particle position is fluctuating, due to the confinement of this potential, it will eventually attain a time independent equilibrium distribution for its position, which is denoted by pi of x comma th. So initially it is at an equilibrium corresponding to the temperature th. Now what we will do is, we will change the bath temperature instantaneously to Tb. So you can think of it like this. So you consider this setup and you attach a different heat bath to it. So the system will be driven out of equilibrium until it reaches the equilibrium distribution corresponding to the new temperature Tb. So we do this experiment several times, but in each of the time, what we will do is we will choose a different temperature for the heat bath, but all the quenched temperatures, final temperature would be the same, and we are interested in the relaxation time of the system. So in this experiment by John Bakehofer's group, they showed that there is a role that this potential plays in the relaxation dynamics. So consider this first case A over here. So this is the case where the potential is symmetric. By symmetric I mean that the domain widths of this potential with respect to the origin is equal. So in the first case x max is equal to x mean. So what they are doing is they are measuring the relaxation time as a function of the initial temperature from which the system had started equilibrating. What they found was that with the increase in initial temperature, they find an increase in the equilibration time of the system. But then they show an anomalous behavior in the relaxation of this kind of system due to the change in the potential landscape. So in the case B, they make the potential slightly asymmetric. So the domain widths are not equal now. So x max is not equal to x mean, and in that case they find an anomaly in the relaxation time. So here what they showed was that if you increase the initial temperature, there is a drop in the relaxation time. If the further increase the asymmetry in the potential, there is a region where there is a drop in the relaxation, and then after that range, there is an increase in the equilibration time with the increase in the temperature. So that is a normal behavior after that. So we are interested to understand this kind of anomaly in this kind of system, and a simple model is always helpful to underpin the cause of such effect. So we consider a double piecewise linear double well potential. So the particle is diffusing in this potential, and since we are interested in the position distribution of this particle, this kind of model gives us the exact result for this distribution. So here is the protocol for the study of the Pemba effect in this kind of setup. So this is our system. We attach a temperature bar Th to this, so that initially it is at an equilibrium distribution pi p, and then there is an identical copy of this setup where it is initially connected to a different temperature bar Tc, and it attains an equilibrium distribution pi q corresponding to the cold temperature Tc. Now we quench both the system using a common temperature bath. So Tb would be the same for both the system. So and eventually it will relax to this final equilibrium distribution. Now we are interested in the relaxation of both the systems to the common state, and we would like to ask if the hotter system can actually cool faster. So in order to track the system from one equilibrium state to another equilibrium state, we will use this distance measure L1. So it basically measures the instantaneous distribution of the system with respect to the final distribution. So there are two ways to analyze this. In one case, we look for the phase space of the system where this kind of anomaly occurs. So for this kind of setup, we can actually calculate the entire phase space where this kind of phenomena occurs, but we are not interested in that for this talk. Rather we'll look how the potential landscape and the initial temperature is playing a role for this kind of anomaly. So here I have taken two different cases for the potential landscape as shown in figures A and C, and in figures B and D they show the population distribution of the Brownian particle in this potential landscape. So the blue one corresponds to the population distribution of the Brownian particle when it was initially equilibrated at the cold temperature. Red one is for the hotter system, and the black one corresponds to the final distribution where they would like to reach. So in the first case we have considered a potential landscape which has a significant barrier height between the two wells. Now in this case, when we look at the population distribution of the Brownian particle, we find that the colder particle has a slight localization in the local minima. So this much population has to hop over the barrier in order to attain the final equilibrium state, and this relaxation due to the thermal process is very slow. On the other hand, the hotter particle, if you look at its population distribution, it has a uniform distribution over the entire landscape. So it says that it doesn't feel this potential landscape and it can relax to this final equilibrium much faster than the colder one. That's why we see a Pemba-like behavior in this case. On the other hand, if we consider a flat potential, So there is no such barrier height between the two wells. And in this case, if you look at the population distribution of the Brownian particle, you find that they have a similar distribution. And since the colder particle is initially closer to the final cold temperature, it relaxes faster, and we do not see such anomalous behavior in this case. So the presence of a high barrier is actually playing the role of a metastable state, due to which the colder particle is cooling fast, the hotter particle is cooling faster. So just one. Yeah. So we are also interested in some in microscopic parameters that can actually capture this kind of relaxation, and we have also done some analysis in many particle setups, so which we are not discussed, but it is highly counterintuitive in this case because there is no such metastable state in this case, and this kind of setup will might have possible practical applications also. So this was done with Prasad, Oren and Rajesh. And so this kind of study for the anomalous behavior would certainly be interesting because this can lead to better understanding of better understanding of the relaxation behavior in non-equilibrium systems. So with that, I would thank you for your attention.